The first step in the traffic detector design process is choosing the detector that is best for your purpose. A number of state agencies have established design policies or standard plans, while others offer optional plans. The following information can be used as a guideline for selecting a detector. There are 4 criteria for selecting a detector. 1. Selection based on operations. 2. Based on applications. 3. On installation. And 4. Selection based on maintenance. As we discussed in the first video section, there are certain design differences among the 2 principal types of detectors that affect their suitability for certain situations. When choosing a detector based on its operational characteristics, consider its weak points as well as its strong points. For example, magnetic detectors, capable of passage detection only, are inappropriate for operations requiring presence detection. And magnetometers cannot be used with NEMA controllers in situations requiring a delayed call capability, a feature they do not possess. When selecting a detector based on applications, choose a loop detector or a magnetometer for detecting a large area and a magnetic detector for a small area. When basing your selection on installation, 3 things should be taken into consideration. First, existing equipment. To keep costs down, examine the equipment currently at the site. For example, if a suitable pole is already at the location, you might choose a radar or ultrasonic detector over a loop detector. Second, pavement. The type of pavement and its condition can influence your detector selection. Third, cost. Consider the life cycle cost of the detector. Compare the benefits of choosing an expensive detector with low maintenance costs versus a less costly detector with a high repair or replacement charge. Traditionally, cost of maintenance has been the primary consideration for selecting a type of detector. For example, the rugged, low-maintenance magnetic detector is still popular despite its limited capabilities. However, when selecting a detector based on maintenance differences, remember to consider the amount of time that will be spent on maintenance as well as the cost of maintenance. Once the detector type has been chosen, the next step in the design process is to select the type of timing intervals for the intersection controller. These timing parameters directly relate to the detector type and low speed versus high speed approaches. Normally, in an actuated phase, there are 3 timing parameters in addition to the yellow and red intervals. First, there is the minimum green, or initial interval. Next is the passage time, also known as the vehicle interval, the extension interval, or the unit extension. And the maximum green interval is the last timing parameter. The minimum green interval is the amount of time a detector allows for a stopped vehicle to accelerate and move into the intersection. When a type of point detector, such as a 6x6-foot loop detector, is used, the minimum green interval allows a vehicle stopped between the detection point and the stop line to comfortably move into the intersection. Presence detectors with loops ending at the stop line require a different timing approach. In this situation, the minimum green interval can range from 0 seconds for a turn lane requiring a quick response to a longer period of time for straight-through vehicle movements. The passage time interval accommodates the queue of vehicles following the lead vehicle through a green light. The passage time defines the maximum apparent time gap that can occur between vehicles without losing the green signal. At intersections using a loop detector, the loop is activated by a vehicle passing over one part of the loop and deactivated by a vehicle leaving the loop. Therefore, the true passage time gap is reduced by the amount of time that it takes a vehicle to travel across the loop. Another factor to consider when determining the appropriate passage time interval is the number of approach lanes containing detectors. In this situation, a single lead cable connecting detectors of the same phase and function to the detector amplifier can present a distorted picture to the controller. Many current NEMA controllers have a predefined minimum green interval. If no further vehicle movements or actuations occur, the minimum gain becomes the total gain. If, however, there are further actuations, the passage time interval extends the green signal until this gap is exceeded or until the maximum green interval is reached. When determining the appropriate passage time interval for a site, consult your traffic detector handbook concerning the impact of using long versus short loops. The maximum green interval is the time limit a phase can hold the green. This interval begins timing from the first call the controller receives from the cross street. When the signal is properly timed, with appropriately short passage time intervals, the maximum green time period will not consistently be reached unless the intersection is badly overloaded. Several actuated controllers are capable of providing 2 maximum intervals per phase, allowing more flexibility during peak traffic periods. In addition to phase timing, you must consider the speed of the oncoming vehicles. Approaches of less than 35 miles per hour are considered low-speed approaches. Approaches of over 35 miles per hour are referred to as high-speed approaches. And the detector design for a given approach of any speed depends on whether the controller phase memory has been set for locking or memory on detection versus non-locking or memory off detection. This locking feature allows a vehicle call for green to be remembered or held by the controller until the call is satisfied. The call for green is remembered even if the vehicle continues past the detection area, such as a car turning right on red. In the non-locking mode, the controller forgets or drops the waiting call as soon as the vehicle leaves the detection area. Locking detection memory is associated with small area or point detectors, such as a 6x6 foot loop detector. Often referred to as conventional control, locking memory with point detection includes a preset minimum green interval and a common value passage time. To accommodate different approach speeds, you should locate these detectors 3 to 4 seconds of travel time, that is, up to 170 feet from the stop line. This single detector approach reduces installation costs, but allows false calls for green to occur. Non-locking detection memory is associated with the use of large area detectors, such as a 6x40 foot loop. Often called loop occupancy control, non-locking memory with presence detection provides information on vehicles within the detection area. This configuration screens out the majority of false calls for green, but has a higher cost for both installation and replacement. Loop occupancy control is particularly well suited for left-hand turn lanes, right turn on red lanes, and through lanes with a low-speed approach. There are a number of specific problems associated with high-speed approaches. For example, at a yellow light, some drivers going over 35 miles per hour might brake suddenly, causing a rear-end collision. Others might speed up and cause an accident within the intersection. There are, however, a number of techniques available to avoid creating a dilemma zone of driver indecision during yellow signals. The most conventional technique for a high-speed approach uses a controller with a volume density mode. This type of actuated operation offers variable initial timings and gap reduction timings to accommodate the increased traffic. These additional timing parameters take into account the waiting vehicles behind the first one in line, as well as the wait time of the vehicles on a conflicting phase. Consult your handbook for further design possibilities. During this presentation, we have discussed the selection criteria of detector design as well as the design considerations. Now, let's discuss loop detector design alternatives for small area detection, large area detection, left turn lane detection, through lane detection, and dilemma zone detection. Small area detection concerns point or passage detection with short loop applications, usually employing a single 6x6 foot loop. For narrower lanes, 5x5 foot loops should be used to avoid splashover or adjacent lane pickup. However, smaller loops are not recommended in areas where high bed vehicles must be continuously detected. Short loop detectors, which detect vehicles upstream from the stop line, may be used in a variety of ways and at varying distances from the stop line. A typical application might consist of one or more short loops near the stop line on the actuated approach of a low-speed intersection. Another application requires spacing a number of short loops well back from the stop line. These loops act as extension detectors for higher speed approaches. Due to the necessity of detecting all forms of vehicles, from bicycles to high-bed trucks, manufacturers have developed quite a number of short-loop designs. Several shapes are in common use, while others are only appropriate for detecting a particular range of vehicles in certain locations. Several states, such as California, specify loop shapes that are acceptable in their jurisdiction. When choosing a configuration, consider the loop shape that will allow maximum detection with the least chance of splashover into adjacent lanes. Large area detection normally consists of a detection zone that covers an area of 20 feet or more in a traffic lane. Primarily presence detection, it registers the presence of a vehicle as long as that vehicle occupies the detector zone. Originally, large area detection utilized a single long loop, which encompassed the entire zone. Today, you can choose long loops, sequential short loops, or wide loops in a large area detection design. Traditionally, the long loop has been defined as a 6-foot wide by 20 to more than 80-foot long single loop with 1 or 2 turns of wire. There are certain benefits and drawbacks associated with each of the long loop shapes. For example, the quadrupole design eliminates the splashover problems of the other shapes, but has difficulty detecting high-bed vehicles. And the lengths of all of these long loop shapes increase the chance of detector failure caused by pavement cracks and joint movements. Refer to your handbook for more information concerning long loop comparisons. In response to the problems of long loops, many agencies use sequential short loops for large area detection. Emulating long loops, these short configurations provide excellent detection of smaller vehicles with a much lower failure rate and less splashover. The sequential short loops commonly consist of 4 6-by-6-foot square or diamond-shaped loops separated by 9 or 10 feet. This multiple loop configuration is equivalent to a 51 or 54-foot long loop. The shape, number, and layout of the sequential short loops are determined by the requirements of each specific site. Wide loops are used by some agencies to cover wide lane or multiple lane approaches. Usually 6 foot in length in the direction of the traffic flow, these loops can measure up to 46 feet wide for a 4-lane approach. Not recommended, wide loops frequently fail due to pavement fractures, and a failure anywhere on the perimeter takes the entire loop out of operation. Very large loops of up to 30 feet wide by 60 feet long have been successful, however, in providing an extension of green time during congested periods at certain sites. Responding only to saturated conditions within the loop, this detector application is appropriate for unpredictable locations, such as exits from shopping centers and from industrial plant parking lots. The next loop detector design alternative is left-turn lane detection. Positively affecting the capacity of an intersection, left-turn lane detection reduces unnecessary green time and sometimes the need for left-turn arrow indications. In our left-turn lane example, a 6-by-30-foot presence detector loop is used and the controller passage time is set at 2 seconds. If shorter loops are used, compensate by adding more passage time on the controller. Occasionally, drivers who have proceeded past the stop line to wait unsuccessfully for a gap in the traffic will be stranded. The controller may skip the turn arrow in the next cycle because it cannot sense a vehicle past the detector. To prevent this situation, some agencies extend the loop 1 to 6 feet beyond the stop line. Also, when the left turn demand requires 150 feet or more of storage space, or when higher approach speeds require longer deceleration lanes, the left turn lane layout should include an advanced detection loop. The detection of vehicles in through lanes depends on the approach speed and the controller operation type. Detector designs for through lane detection include single point detection, loop occupancy detection, and high speed point detection. Single-point detection is the simplest form of through-lane detection used for actuated controllers. Located 2 to 4 seconds of travel time in advance of the stop line, a point detector requires very specific controller timing. Appropriate primarily for low-speed approaches, this type of detection is popular for the side streets at those intersections using a more complex detector on the major arteries. Loop occupancy detection, generally chosen for low-speed approaches, uses two basic configurations located immediately upstream from the stop line. The single-loop configuration is 50 or more feet in length. The second design consists of a sequence of short loops, usually 4 short loops. When loop occupancy detection is chosen for large detection areas, this alternative requires the installation of additional long or short loops. High-speed point detection requires a more complex relationship between detector and controller. Volume density control, which relies more on controller function than on a complicated series of detectors, is popular for high-speed approaches. This technique specifies the installation of one point detector per lane, placed 5 to 10 seconds from the stop line. One drawback to high-speed point detection is its potential to place vehicles within a dilemma zone during the yellow change interval. Dilemma zone detection is a problem that has plagued designers as well as operations and safety engineers for years. However, your traffic detector handbook provides a variety of alternatives to address this issue. Unlike the last two systems that are successful predominantly in low-speed situations, multiple detection systems accommodate a wide range of approach speeds. The three commonly used techniques for determining the placement of the multiple detectors, the Byerly method, the Winston-Salem method, and the southern section of ITE method, are discussed in detail in your handbook. They differ primarily in the number of loops used and in the spacing of the loops. During the design process, you may require information concerning special applications, such as bicycle detection or vehicle counting. Or you may want information about magnetometer and magnetic detector configurations. Please consult Chapter 4 of your handbook for this information. Now that we have examined the detector design process, let's proceed to Section 3 for a discussion on detector installation.